So, first of all, thank you for the invitation to speak here. Until about a year ago, I was not doing anything that was in any way related to convex analysis or honestly probability as well. And this talk is about the topic that somehow lured me into thinking about convex functions and how to relate them to probability questions. It's originally it stems from a very applied question. So you have a target distribution that has a nice density. We'll discuss what we mean by nice later, but the important thing is that we don't have, when you think of a probability distribution, especially when you're programming or something like that, you could think of it as a machine that produces samples from it, but you could also think of it as a function that you've programmed that just tells you the density at a point. And that's the framework that we're going to take today. For us, the density is just a function that I can evaluate it at a point and I get the density at the point. However, oftentimes you want to go from this density, which is just a function coded into your computer, into samples. So we want to find algorithms that take as an input a function, a density, and as an output, they produce something that is samples from this distribution, or at least something that looks very close to being samples from this distribution. And we want those algorithms to be general purpose. And by general purpose, what I mean is that they're not going to look into the particular structure of the density function. They're just going to assume that it's something generic. And they're only going to have access to the value at the point. So they're going to evaluate it and get the value and maybe evaluate the gradient. Why do we want to do something like this? Because this, this problem of sampling shows up all the time. From physics to statistics to machine learning, this question of, okay, now I know what I want to sample from, but how do I do it? Shows up all the time. And it shows up so much that there's a lot of people that spend all of their careers building fancier and fancier algorithms to do that. One of the more traditional ways to do it is by simulating a Markov chain where you have proven that the stationary distribution is the one that you want. You could also do rejection sampling, which is you sample from a distribution that you believe is very similar, and then you drop the samples with certain probabilities. You could start with a known distribution and then just apply a function to it to get what you want. There's a lot of ways of doing it. And the hard thing is knowing a priori which one's going to be the best. And in this talk, we're going to go to the simplest setting and try to understand it completely. Understand how hard it is to sample and find algorithms that actually do it. So in order to define optimality, I said that we have nice densities. What are nice densities or nice functions for us? For us, they're going to be log-concave functions. So they're going to be densities that are proportional to e to the minus v, where v is a convex function. And what is the optimal algorithm? Well, this is a very ill-defined question because I haven't told you what optimal even means. And for me, optimal is going to be about how many times do I have to ask for the value of this density. So I'm going to try to minimize how many times do I query v and grad v. Of course, by changing variables, this is the same as querying the density and the grad of the density. It's just more convenient and more numerically stable to keep v in the computer and not the density. So we want to find ways to produce things that look like samples from a distribution and minimize the number of queries. A naive approach would be to basically query this density in a big grid and then use this to make whatever simulation. This is very inefficient. We of course want to show that we can beat naive algorithms first learning all the function. So when we do this, we keep in mind as a dream to copy what happens in convex optimization. Convex optimization, we have a family of bounds that were pioneered by Nesterov, where they're able to show that optimizing a convex function takes a certain amount of samples. He provides an example, what he calls the function that's hardest to optimize. But then he also provides an algorithm that works for that function and that achieves the same complexity. And it's kind of a beautiful part of more pure mathematics or more proof-based mathematics, because it was by first finding the lower bound and not being able to improve it that they realized that, well, maybe we're missing a better algorithm. So kind of the hope is that, well, maybe if we really understand who the enemies are by finding lower bounds, we can then build better algorithms. And we're going to copy it, and we're going to basically copy, pick the setup as analogous as we can. So we're going to start with a density that's log-concave, because that's the major analog of convex functions. So with a convex potential, and I'm also going to ask that it's strongly log-concave and smooth. What this means, it's similar to things that we've already seen these days, is that I want to get the Hessian, and I want to bound it above and below. So I want to, this quantifies how far I am from being Gaussian, more or less. Like if this k had to be 1, then it would be a Gaussian. So this tells you how much room do you have to not be Gaussian. Okay, so now we can state the problem exactly. So I have a distribution, strongly log-concave, and I want to produce a sample that's not too far in TV. Why TV? It doesn't matter. It turns out that if you pick Fisher, Wasserstein, anything else, you can prove exactly the same theorems. And using query access to V and grad V. The question is, how many queries does an optimal algorithm take? And that's going to depend on the dimension. It's going to depend on how bad my distribution is, and it's going to depend on how good I want my results to be. In this talk, I will assume that we want something that's good, but not necessarily perfect. So I want something that's within 1%. I want a sample from a new distribution that's not going to be exactly the same, that's impossible, but it's within 1% of being correct. I only want to produce one sample. This one's a bit unrealistic. If you look at how most of these algorithms work, or at least the Markov chain-based algorithms, they take a time to warm up. You have these theorems that tell you, I run this Markov chain and it converges to a stationary distribution, but you first need to run for enough time to reach a stationary distribution, and then you can produce a lot of samples very cheaply. So what we're doing today is only caring about the time until the first sample. So in that regard, some algorithms are bad, but better than what this theorem would tell us. And the last one is what I'm going to call the post-optimization hypothesis. If you have something like this gives you, sampling from rho gives you a pretty good idea of where the minima of the potential is. If you have a function that's e to the minus v, it's going to be concentrated where v is small. So if I sample a couple hundred from them, I will get a good enough idea about where the minimum is, and I can use that to start an optimization procedure. So we know from here that sampling, producing samples is going to be about as hard, at least, as optimization. Sometimes optimization is harder, but we want to see the sampling part. So we will assume that you know where the minimum of the potential is, or where the mode or average of the distribution is. You know roughly where you expect the samples to come from, but now you want to produce samples from it. So in this setup, we have a bunch of known algorithms that work as following. As you see, the first algorithm has a lot of words in the name. What that basically tells you is that there's been a lot of people that have gotten the same algorithm and improved it over and over. And the only thing that matters for us today is that it's polynomial in both this eccentricity constant and the dimension. However, there's other algorithms that are basically based, so these distributions, these log-concave distributions, are not Gaussians, but they look like bumps, morally. So you can do a procedure where you get your bump and you make it sort of round first, and once it's round, you sample. It turns out that these rounding algorithms are very effective if you start with something very eccentric. They take a lot of time in the dimension. They're very bad in the dimension, but if you have low dimensions and very high eccentricity, these rounding approaches are very, very efficient. So we know that there's at least two regimes where our algorithms are very different. And the goal of this talk is to show that in the extreme case where kappa is very big, this regime is sharp. That the algorithms that we have in these very kind of low dimension, very extreme log-concave distributions, this log kappa over there is as good as you can.
What was kappa?
Kappa is the eccentricity. It was the so we had this squared. So it's how, and again, since it's log-concave, it's morally equivalent to the condition number of the covariance matrix of your distribution. So it's an upper bound, if you want, to the condition number of the covariance of your distribution. So we're going to show that in the case where your distributions are very wide, you can there's a log kappa that you cannot beat, but it's what it is. Okay, so the type of result we're going to talk, we're going to consider the class of potentials that have this sort of eccentricity, and we're going to show the following. If you have an algorithm And this algorithm produces samples that are in TV at most 1% off from your distribution. Then your algorithm takes in dimension 2 and higher at least log kappa samples, and in dimension 1 log kappa samples. There's another algorithm in dimension 1 that also reaches this log kappa, so this is sharp. You can also show that sampling in higher dimensions becomes harder, which tells you that this log kappa is there in every dimension. We just don't control how the constant grows with the dimension, and that's honestly like the thing that like the obvious next step from the results I presented today. So what's the strategy to prove something like this? The real hard part here, the real enemy, is that we're not assuming anything at all about the algorithm. Like, the algorithm is just something that someone's come up with, and we want to prove that works for basically any algorithm. So you start with a family of distributions that are log-concave. In our case, after doing a little bit of cheating for the talk's sake, there are going to be some nice piecewise linear potentials. And then we can smooth them out by modifying and make sure that they are in this class. But for the sake of the talk, I'm just going to chop them off to be piecewise linear. And then we're going to pick a property. A property is something that we want to learn about the distribution. It could be the mean, it could be the variance, it could be the largest eigenvector of the covariance matrix, or maybe if the distribution is finite, the challenging property would be to guess which distribution did I give you. So I'm going to give you a property. I'm going to give you a distribution and a property, and I want you to guess the value of the property for the distribution. But what I want for the property is two things. I want that it's very cheap to learn this property from samples. That basically, if I give you 20 samples from this distribution, you can guess the property very efficiently. This is true, for example, for the variance. If you have a log-concave distribution, estimating the variance is very easy. But I also want it to be very hard to estimate just by queries. And that's going to be the hardest part. So we have to find a property and show that it's really hard. Like, we will have to use some information bounds and showing that it's really hard to obtain information about this property by querying the algorithm. That it's very easy to obtain this property from samples, and then it's hard from queries. Okay, so samples. I can pay for this property very cheap with samples. It's very expensive to pay it with queries. That means that samples themselves are very expensive, and that's basically what we do. We know that if I create S samples and I spend N queries per sample, then I will succeed at learning my properties, so we get an inequality of this form. That the amount of, this is the amount of queries that I need per sample. It has to be bounded by the difficulty of the learning property from the problem point of view. And so the rest of the work is just finding the right properties and right functions. In order to do that, I'm going to do a massive simplification. I am going to stop talking about log-concave sampling, and I'm going to move to convex set sampling. The problem is the same, except now I'm sampling from uniform distributions on convex sets. And the only thing that I can ask you about a convex set is whether a point is inside or not. So we're going to build an order, like you're going to get a function, which is the indicator of the convex set, and you can query it however many times you want. When you query it, you get an answer of is the point inside or not. And you want to produce a uniform point, a uniform sample from this convex set. And the question is, how can we do that, or how can we show that this problem is hard? Now, we do have an information theory bound. Every time you're just receiving one bit. So the query problem only gets you one bit of information per sample. So now we just have to find a property that has a lot of bits and that you can learn easily from samples. What's going to happen with log-concave? I'm going to build some piecewise linear potentials that are going to be very similar to these indicator functions. They're essentially going to look the same from a sampling point of view, but I'm going to build them piecewise linear in such a way that if you look at a point, they all look the same. They all have essentially the same slope. In such a way that you again gain one bit of information. So basically the whole gist is that there is a way to transfer these results for convex sets, which are easy to prove because you're naively just getting one bit per sample, to the much more complicated log-concave setting, where the information is a priori all over the place because you have a smooth function. You don't know what information is hiding in which part. Okay, so how do we do this in the convex set? So we start with a family that has a lot of convex sets. And, oh, I forgot to say that, and this is kind of important. The analog of the property, of this property for convex sets, They're convex sets that contain that contain a ball of size k to the minus 1 and are contained in a ball of radius k. This again is sort of bounded the eccentricity of the set, so this is the analog of that property in the convex set setting. Okay, so what I'm going to do is I'm going to find a lot of convex sets that are separated. The fact that they're separated essentially tells me that I can distinguish which set I come from by just getting a couple samples. So that's the first thing I want from my family. And then my interesting property is I just want to guess which set you came from. It turns out that once you have that property, guessing most of the information or guessing with high probability which set you come from turns out to be quite easy. Like getting a finite amount of samples, you can guess with having a positive amount of information. We work with information theory because it's a bit easier, but you should be able to do like high probability estimates as well. So it turns out that learning our property takes us like a couple samples, but it's very hard to learn which set I come from queries. Why is that? Well, I have m sets. In order to encode m sets, I need log m bits. So I'm going to need at least log m, log cardinality of m bits in order to learn, to have a decent chance at guessing the set I'm coming from. And that's basically what we get. We get that the number of queries is at least the logarithm of the cardinality of the set. How do we build those sets? Well, let's start with dimension 1. I have to pick a lot of sets. In dimension 1, there are intervals. Convex sets are intervals. They contain a ball of radius k to the minus 1, and they're contained in a ball of radius k. And I want them to be essentially disjoint. The only way I can do that is by shifting scales. If I have like an interval of size like 1/2, 1/2, and then an interval of minus 1, 1, their indicator functions, they're not exactly disjoint, but when you look at the difference of the indicator functions, it's big enough. And that's basically what we do. We consider all the possible scales. How many scales do I get? Log kappa, because I'm going from 1 over kappa to kappa. So I have log of kappa squared, which is log kappa. From here, what you see is that sampling from convex sets in dimension 1 takes you at least log kappa. Because log kappa was the number of sets, and then we'll have to take a log because of information theory. This is the result that we also get in the log-concave setting, which is sharp, and it's also sharp in the convex setting. Now, let me do a detour for a second and remove the hypothesis that our set is centered at the origin. Let's forget about that. If we forget about that, we get the uncentered case, where now I can consider intervals, not only the dyadic intervals from before, but I can consider literally disjoint intervals. How many literally disjoint intervals can I put? Well, each of those size kappa minus 1, and they have to be all inside of a ball of radius k. I'm still keeping this property. So I can put k squared of them. So the number of, the size of these like disjoint, how do you call this? It's sort of like the packing of a packing of this certain metric space with the TV metric, but the amount of disjoint sets that I can put is k squared. So I get that the amount of information that I need and the amount of terms is log k. So now what we're going to do is we're going to look at dimension 2 in the centered case, and I want to convince you that dimension 2 in the centered case and dimension 1 in the uncentered case are the same problem. Okay, so what do we do in dimension 2? In dimension 2, now we are centered, so we have to contain this little ball around the origin and clean this. We build a bunch of rectangles. A rectangle, and if I pick the angle to be, so this is approximately k, and this is k to the minus 1, so I can put roughly k squared rotated copies of the same thing, and they're essentially disjoint again. What this tells me again is that I can, the difficulty of sampling from dimension 2, at least in this convex setting, is going to be at least log k squared, which is log k. Why did I claim that this problem was similar to the uncentered one in dimension 1? Well, I can just draw a line here and look at the intersections of my packets with the line. If I pick a generic line, they should be mostly disjoint, and what I'm going to get is again a copy of the example in dimension 1. And that's the way we're going to build the higher, like the two-dimensional counterexample, by first building an uncentered example in dimension 1, and then sort of radially lifting it, or like lifting it in a homogeneous manner to higher dimensions. But this is basically like, this is how you guess what answer you should be getting, and then you actually have to go and build potentials that hide all of the information to transfer this from this case to the actual log-concave case. How do we do that? Okay, so we start by remembering that every convex set can be written as an intersection of half-planes. In our case, we're going to write it as a finite intersection of half-planes. And in order to build a potential, we want to build a potential that's 0 in our convex set and very big outside. So that when we take e to the minus this, we get essentially the indicator function of our convex set, and we can repeat all of our theorem. Our potential is going to be the maximum of a lot of support functions, which are going to be linear functions that exit the set. How are we going to build these functions? Well, the kind of the trick is to not be too efficient. If I want to do an interval, I want to build a potential that's only 0 in this interval and big outside, I can just extend the function like this, and it works. However, if you just have a function like this, and you have like the smartest algorithm would just realize that it's here, and just come here and learn immediately that one end of the interval is here, and also the other end is here. So just being naive like this is not going to beat smart algorithms. The way to solve that is to add a lot of noise, add a lot more garbage on this convex potential, so that it completely confuses the algorithm. Once you have this piece of linear thing, in order to go back to the hypothesis of the theorem, you have to add a little piece because we wanted it to be strongly convex. You have to modify it so that it's smooth. You have to make it big so that e to the minus this is essentially an indicator of the identity. But all of this is just like, for us today, it's just a technicality. It's like, there is a way to upgrade from these piecewise things to things that satisfy like the smooth concavity of the problem without paying anything we're not allowed to pay. Okay, so how do we build these linear potentials in dimension 1? Remember, in dimension 1, our intervals were just dyadic intervals, and I have to build a potential for each interval. The way I'm going to do it is I'm going to pick a support function. This support function over here is essentially a selector for an interval of size 2 to the k. But what I'm going to do is I'm going to take the maximum between my selector and the selectors of every possible bigger interval as well. When I do that, I get a function like this. So I'm selecting the interval minus 1/4, 1/4. If I just wanted to select this one naively, I would pick this function. But then I also take the maximum with the selector of the next scale and the selector of the next scale and so on. What does that tell me? Well, if now I query this function, let's say at 2, I have no way of knowing if I came from this, from the minus 1, 1, from the minus 1/2, 1/2, or from the minus 1/4, 1/4. So this effectively hides the information. In this case, you can show something quite stronger. Here, I've drawn the potentials with that form for minus 1, 1, minus 1/2, 1/2, minus 1/4, 1/4. It turns out that if you look anywhere, there's at most, I mean, in this case, it's kind of stupid that these functions take at most 3 values because I've only drawn 3 of them. But it turns out that if you drew every possible function of this form for every interval and you looked at any point, this function can only take 3 different values. So this brings us back to the information theory approach, except now instead of just learning a 0 and a 1, we learn one of 3 possible values. This is still like roughly 1.5 bits. So by the same algorithm, by the same argument, I'm learning at most 1.5 bits per query. I have a lot of things that I have to distinguish from, log m again. Okay, what do we do in the uncentered case? We do the same thing except we consider dyadic intervals. What are dyadic intervals? They're intervals of length 2 to the n. But where the endpoints also have length 2 to the n, basically you start with your real line, and you chop up, let's say this is 0, this is 1, you chop up in 2, and then at the next stage you chop up in 2, and so on. And how am I going to build the selector for this little guy? I'm going to select the maximum between this selector, and this selector. So it's essentially the same, but I have to do it in the uncertain way. So I define all my possible dyadic intervals. I already take my k so that like every interval I care about is dyadic. And I build my potential again by taking a maximum amongst a lot of selectors which are every selector that contains my interval, so it doesn't hurt me, it's still 0 only where it has to be. And I get something like this. And the situation here is the same. If you're far enough, you only see a big selector. Because you're taking the maximum between things at the different scales, and when you're far away, you only see the selector of a size comparable to the scale you are. And you're in this kind of like tautological situation. Here I've thrown a bunch of them again, where if you're far away, they all join together and become the same thing. These two are closer, so they become the same thing closer. And they're only different when you're close enough. And you end up in this paradoxical situation where you only learn information at the same scale where you already had information about. And sometimes you get lucky and you get a little bit more information, but it's kind of chat. You basically get no information, or at most 1 bit of information per query. And it's the same thing. Now, we cannot say that the number of bits you learn is at most 1, but in expected value it is, and then by some concentration tricks, you're done. How do we go from here to higher dimensions? The answer is actually quite painful, but we're going to pretend it's not. And I'm going to do the very simplified thing that almost works. So you extend your function in 2 variables, almost like in polar coordinates, and you get something like this. This function satisfies everything that we've said so far. It would almost work, except for the modification step. The modification step kind of blurs all of the information in the origin, and it turns out that doing a single query at the origin, you can learn everything you want, which is a bit of a problem. But there's a way to solve that. But I don't have time to show it, but you have to do a small variation of this proof, of this construction, and then you can extend it to dimension 2, and then to dimension higher just by monotonicity, and we get the result. So where do we go from here? The first thing that we would want to do is show that at least when the eccentricity is large enough, we can get some polynomial lower bound in the dimension. So basically, it's like, how do I repeat this construction in higher dimensions? Just a hint, doing tubes in higher dimensions doesn't work. You have to do at least d over 2 dimensional subspaces, because you need a lot more, you need to have a lot more pieces than you would think otherwise. So it's just tubes doesn't work, but half-dimensional subspaces, at least back of the envelope, should work. What else? What about the number of samples? You should be able to say something out of this theorem. I don't know what, but you should be able to extract something out of this theorem. And the last one is that in high dimensions, the best results we have come from Gaussians. We have in the same paper that this comes from, there's some result in very high dimensions where kappa is small and the dimension is high, and we show that sampling is hard because of Gaussians. Gaussians are too nice, they're the nicest distribution, they can't be the hardest to sample. So the question is it true at all that Gaussians are the worst enemy at some point? And that's something that I would really like to understand. So yeah, that's everything I wanted to talk about. Thank you very much.